Hello everybody, my name is Ethan. Welcome back to the channel where today we are hopping back into the machine learning course on Codecademy. In today's video, we are going to be doing support vector machines. In the previous video, we covered naive Bayes classifier and everything that went along with that. And then in the video before that, it was Bayes theorem. If you missed those two videos, those are pretty crucial into the supervised learning 2 module. So we're going to kind of try and get into that. It looks like we're going to have a kind of a chapter and then obviously a quiz and a project. And then perhaps one more little article that we could maybe sneak into the end of this video, because it looks like then after that we'll get into another section called regularization hyperparameter tuning, I think is what that was, turning, sorry. So I'm just going to hop right into this video. I don't see anything else that I need to talk about really. So we'll start off right away with support vector machines. A support vector machine, SVM, is a powerful supervised learning machine model used for classification. An SVM makes classifications by defining a decision boundary and then seeing what side of the boundary an unclassified point lands on or falls on. In the next few exercises, we'll learn how these decision boundaries get defined, but for now, know that they are defined by using a training set of classified points. That's why SVMs are supervised machine learning models. Again, they use training set. Decision boundaries are easiest to wrap your head around when the data has no features. In this case, the decision boundary is a line. Let's take a look at the example below. Average time to catch snitch, average number of goals. So we can see that there's a definite correlation. There's a line here. Playoff teams or non-playoff teams are up here, and playoff teams are down here, right? And this would make sense. The longer it takes you to catch the snitch, it's going to lower the amount of goals you get. So having a lower average time to catch it and a higher number of average goals obviously is going to mean that you're going to do a little bit better, right? So note that if labels on the figures in this lesson are too small to read, you can resize the pane. This SVM is using data about a fictional game of Quidditch from the Harry Potter universe. This classifier is trying to predict whether a team will make the playoffs or not. Every point in the training set represents a historical Quidditch team. Each point has 2 features: the average number of goals the team scores and the average number of minutes it takes for the team to catch the golden snitch. After finding a decision boundary using the training set, you could give the SVM an unlabeled point, and it will predict whether or not that team will make the playoffs. Decision boundaries exist even when your data has more than 2 features. If there are 3 features, the decision boundary is now a plane rather than a line. So we have a third. We added average broom speed. And so now we have this plane of people, or a plane of guessing, right? As the number of dimensions grows past 3, it becomes very difficult to visualize these points in space. Nonetheless, SVMs can still find a decision boundary. However, rather than separating line or separating plane, the decision boundary is called a separating hyperplane. Run the code to see the 2 graphs appear. Right now, they should be identical. We're going to fix the bottom graph so it has a good decision boundary. Why is this decision boundary bad? So first, we'll run the code just to refresh this. It's going to just pull up the same 2 graphs. If we're answering the question, why is the decision boundary bad? It's because, I guess I should say, data points that are classified in the same class are on either side of the decision boundary. So we consider these blue points playoff teams, right? We're going to say that we're fixing this one. Sorry, they're identical, but we're fixing this bottom one, right? So right now, we can see that the decision boundary kind of goes in between points that are in the same classification when we'd want all of one class on one side and all of another class on another side, right? So let's shift the line on the bottom graph to make it separate the 2 clusters. Jesus, I'm having a little bit of trouble talking today. The slope of this line looks pretty good, so let's keep it at -2, but we want to move the boundary up, so change intercept 2 so that the line separates the 2 clusters. So to do that, we'll probably move it up a little bit, right? So intercept 2 right now is at 8. We could try 12 instead and see what happens. 12 is okay, but we can still see that there's a little bit of extra stuff, possibly going up to 8. So let's try instead 14 and see what happens. This one's obviously much better. It goes in between both of the clusters. All of the points in one class seem to be on one side of the boundary line. That's exactly what we want to see. Optimal decision boundaries. One problem that SVMs need to solve is figuring out what decision boundary to use. After all, there could be an infinite number of decision boundaries that correctly separate the two classes. Take a look at the image below. Obviously, in this image, right, all of them actually do the job of separating the two clusters, but there are so many valid decision boundaries, but one is best. In general, we want our decision boundary to be as far away from the training points as possible. Maximizing the distance between the decision boundary and the points in each class will decrease the chance of a false classification. Take graph C, for example. The decision boundary is close to the blue class, so it's possible that a new point close to the blue class will fall under the red side of the line. Out of all the graphs, graph F has the best decision boundary line. Run the code. Both graphs have suboptimal decision boundaries. Why? We're going to fix that on the bottom graph. We're going to have to make the decision boundary much flatter, which means we need to lower its y-intercept. Change y-intercept 2 to be just 8. Next, we want the slope to be pretty fat. So, or flat, not fat. Again, I'm having trouble talking today. Change the value of slope to. We can also do a -1. See what happens. That seems to be a little bit too much. Let's try -2 instead of -1. Or it should be greater than -1. So maybe -0.5. That seems to be pretty good. We kind of split it, and they're very equal in distance from the line. Pretty good. Support vectors and margins. We now know that we want our decision boundary to be as far away from our training points as possible. Let's introduce some new terms that can help explain this idea. The support vectors are the points in the training set closest to the decision boundary. Let's introduce some new terms that can help us explain this idea. Yep. Okay. The support vectors are the points in the training set closest to the decision boundary. In fact, these vectors are what define the decision boundary. But why are they called vectors? Instead of thinking about the training data as points, we can think of them as vectors coming from the origin. So we have them coming from the origin here. These vectors are crucial in defining the decision boundary. That's where the support comes from. If you're using n features, there are at least n+1 support vectors. The distance between a support vector and the decision boundary is called the margin. We want to make the margin as large as possible. The support vectors are highlighted in the image below. Support vectors define the margin, average time to catch a snitch, right? Because the support vectors are so critical in defining these decision boundary, many of the other training points can be ignored. This is one of the advantages of SVMs. Many supervised machine learning algorithms use every training point in order to make it a prediction, even though many of those training points aren't that relevant. SVMs are fast because they only use support vectors. What are the support vectors for the SVM picture below? There should be 2 blue support vectors and 1 red support vector. Well, I'd say it's probably this one and probably these 2. Finish defining red support vector, blue support vector 1, and blue support vector 2. Set them equal to the correct points. The point should be represented as a list. So for the red support vector, I'm going to go with 1, 6. So we'll do 1 and then 6. For these 2 blue ones, we have one that is 0.5 and 2. We have another one that is 2.5 and 2. So that's correct. What is the size of the margin? Find the total distance between a support vector and the line by looking at the graph. Create a variable called margin size and set it equal to the correct number. So let's just create a new variable called margin size and set it equal to the total distance between a support vector and the line by looking at the graph. So it looks like there is a distance of 2 between all of them, right? The distance is 2. So I'd say margin size is equal to 2, right? That makes sense. Scikit-learn, now that we know the concepts behind SVMs, we need to write code that will find the decision boundary that maximizes the margin. All the code that we've written so far has been guessing and checking. We don't actually know if we found the best line. Unfortunately, calculating the parameters of the best decision boundary is a fairly complex optimization problem. Luckily, though, Python's scikit-learn library has implemented an SVM that will do this for us. Note that while it's not important to understand how the optimal parameters are found, you should have a strong conceptual understanding of what the model is optimizing. To use scikit-learn's SVM, we first need to create an SVC object. It's called SVC because scikit-learn is calling the model a support vector classifier rather than a support vector machine. So we create a classifier variable that is an object of the SVC with the parameter that kernel is equal to linear. We'll soon go into what the kernel parameter is doing, but for now, let's set it to a linear kernel. Next, the model needs to be trained on a list of data points and a list of labels associated with those data points. The labels are analogous to the, I probably am butchering this word. We haven't done this in a while, so let's hear how to pronounce this. I gave it my best go.
Analogous.
Analogous. The labels are analogous to the color of the point. You can think of 1 as a red point and 0 as a blue point. The training is done using the .fit method. So we would do training points, their labels, and the data, so it would end up looking like this. Calling .fit creates the line between the points. When we go back to the .fit, we use 2 parameters to fit the model. We use the training points and labels. That's pretty standard across all scikit-learn from what I have experienced. Finally, the classifier predicts the label of new points using the .predict method. The .predict takes in a list of points you want to classify. Even though you only want to classify 1 point, make sure it is in a list. In the image below, the predict make a list of points you want to classify. So it would probably be a list of lists if we did multiple points in this case. Yeah, it is a list of lists. So in the image below, you can see the unclassified 2 point as a black dot. It falls on the red side, so the SVM would predict it is red. In addition to using the SVM to make predictions, you can expect some of its attributes. For example, if you can print classifier.supportVectors to see which points from the training set are the support vectors. In this case, the support vector looks like this. Let's start by making an SVC object. We can do this by calling it classifier. Set it equal to SVC with the parameter kernel is equal to linear. I think it might be not kernel, and it's actually kernel. We've imported some training set data called classifiers.fit method, so we can do classifier.fit. We'll first import points and labels. Okay. And we can now classify new points. We're going to classifier.predict. And what we will do is the first 3, 4, and in the second one, we'll classify 6, 7. And we can maybe wrap this in a print statement just so we can see the output. So in the first one, it predicts that it would be 0. And for the second one, it would predict it would be 1. And we kind of said that earlier. We predicted that, or we said that you can think of a 1 as a red point and a 0 as a blue point. So in this case, it's saying that 3, 4 would be a red point, and it's saying that 6, 7 would be a blue point. That's kind of what it's, you can see our eyeball as a human, but it's good that we can do that with a computer. All right, outliers. SVMs try to maximize the size of the margin while still correctly separating the points of each class. As a result, outliers can be a problem. Consider the image below. So we have 2 groups, but we have a couple of outliers here. The size of the margin decreases when a single outlier is present, and as a result, the decision boundary changes as well. However, if we allow the decision boundary to have some error, we could still use the original line. SVMs have a parameter C that determines how much error the SVM will allow for. If C is large, then the SVM has a hard margin. It won't allow for any misclassifications, and as a result, the margin could be fairly small. But if C is too large, the model runs the risk of overfitting. It relies too heavily on the training data, including the outliers. On the other hand, if C is small, the SVM has a soft margin. Some points might fall on the wrong side of the line, but margin will still be large. This is resilient to outliers, but if C gets too small, you can run the risk of underfitting. The SVM will allow for so much more error than the training data won't be represented. All right, when using scikit-learn's SVM, you can set the value of C when you create the object, so C is equal to 0.01. The optimal value of C will depend on your data. Don't always maximize margin size at the expense of error. Don't always minimize error at the expense of margin size. The best strategy is to validate your model by testing many different values for C. All right, run the code to see SVM's current boundary line. Note that we've imported some helper functions we named called draw points and draw margins to help visualize the SVM. So as you can see, this is what it looks like. Let's add an outlier before calling fit. Append 33 to points and append 0 to labels. This will add a blue point at 33, right? So we can do this by going in here and saying points dot append, and we'll append the 33, and then we'll say labels dot append, and we'll do the classifier 0. We're going to just classify 0. And now if we rerun it, we can see that it's going to mess with our stuff a little bit, right? So right now our classifier has hard margins because C is equal to 1. Change the value of C to 0.01 to see what the SVM looks like with soft margins. So in the previous, it was hard margins. Only 1 point was allowed to be on the margin. In this case, though, we see a little bit more soft margins and even one that's a little bit more on the left side. All right, we're going to append at least 2 more points to points. If the points appear on the graph, make sure their x and y values are between 0 and 12. So for one of them, we're saying that we first said that 3, will also append... let's do a 6, 2. In this one, we also want another 0. And then let's do a red one just for fun. Switch it up just a little bit. Let's append something like 2, 8. 2, 8. And we'll classify that one as a 1. When we do this, I see, it doesn't like that I did that. So let's just redo this. Points.append 6, 2. I didn't know you could not use the append function like that. And then we're going to have to do it a couple more times here with labels.append with the value of 0 and labels.append with the value of 1. And then we'll get rid of that. And we have done that now. Let's play around with the C variable to see how the boundary changes with your new points added. A value between 0.01 and 1. So let's change it to 0.5 just to see what happens now. A little bit more of a harder boundary now, because we can now see that there's 2 points on the line. Let's now just ultimately try a C of 1 once again to make it hard boundaries. And it looks very similar. I don't know if anything changed between 0.85 and 1. All right, kernels. Up to this point, we've been using data that is primarily linearly separable. This means that it's possible to draw a straight line between the two classes. However, what would happen if we came along a data set that wasn't nearly or linearly separable? So obviously we have an inner group and a outer group, right? It's not really possible to draw a straight line. Luckily, SVMs have a way of handling these data sets. Remember, when we set kernel equal to linear, when we're creating it, kernels are the way to create a decision boundary. So we can also use linear. There's some other options here. However, it's not drawing a line, right? Let's take a look at the power of kernels. We've created a data set that isn't linearly separable and split into training and validation. So we'll create a new classifier object, SVC. And we're saying that kernel is equal to linear. And now it wants me to call the fit function and fit it using the training data and training labels. We can now call classifiers.score function using the test. I guess they're calling it validation data and validation labels. And we want to print this out. So it looks like the model is 43% accurate. That's not a really good accuracy. Actually, that's pretty bad. The classifier is getting right less than 50% of the time. Change linear to poly instead, and add the parameter degree equals 2. So we'll also add the parameter degree equals 2. Run the program and see the score change. Oh, now it's 100% accurate. That's obviously a big change. So that ended up working out really nicely. Every single point in the validation. Let's go learn. All right, polynomial kernel. That kernel seemed pretty magical. It was able to correctly classify every point. Let's take a deeper look at what it's really doing. We start with a group of non-linearly separable points that looked like this. Right, so we had this initial, or not initial, but this inner group. We also have this outer group of points. The kernel transforms the data in a clever way to make it linearly separable. We use a polynomial kernel, which transforms every point in the following way. So we get x and y is now equal to the square root of 2 times x times y times x, and then x squared, and then y squared. This kernel added a new dimension to each point. For example, the kernel transforms the point 1, 2 into 2 times the square root of 2, 1, and 4. If we plot these in a three-dimensional plane, we get the following graph. Now we can see, oh, well, there's this, and there's this whole group. Now we have a plane in between them. Look at that. All of the blue points have scooted away from the red ones. By projecting the data into a higher dimension, the two classes are now linearly separable by a plane. We could visualize what this plane would look like in 2 dimensions to get the following decision boundary, right? So we have now the decision boundary looks like that. In this exercise, we'll be using a non-linearly separable data set similar to the concentric circles above. Rather than using a polynomial kernel, we'll stick to the linear kernel and do the transformations ourselves. The SVM running a linear kernel on the transform points should perform identically to the SVM running a polynomial kernel on the original points. To begin, at the bottom of your code, print training data 0 to see the first data point. All right, we can do that pretty easily. We'll print training data at the index of 0. And we see that this is what the point looks like. Let's transform the data into 3 dimensions. Begin by creating 2 empty lists called new training and new training and new validation. So we've created the 2 empty lists here. Now we're going to loop through every point in training data. For every point, append a list to new training. This list can contain 3 numbers. The square root of 2 times 0 times 0.1, the 0.0 squared, and 0.1 squared. Okay, so we can now do that by doing, again, a for loop. So for point in training data, I am going to quickly just print point, and then I'm going to break. just so I get a look at what the first one looks like. And again, it's the same one that is the print, so I'm making sure that my for loop is doing what I want it to do, right? So we can now get rid of this. Point is doing exactly what I want. So now what it wants me to do is find make a list of the new objects. So we'll first say we'll create a new list object called new list, set it equal to an empty list, and this we're going to create for every single one or every single point in the training data. So the first part of the list is the square root of 2 times the point of 1 and point of 0. So we can do this by just appending it. So we do new list dot append, and inside this we're going to do the square root. Do we have, I don't know if we have, I think we can do square root. I guess it doesn't really matter. We can just do 2 to the power of 0.5 times the point at index 0 times the point at index 1, index 1. And we're going to do a couple more appends here, list dot append. And in this one, we are just going to do point 0 to the power of 2. And we'll do one last one where we append the point at index 1 to the power of 2. Now what we can do is create and we're appending it to new training. So new training dot append new list. Perfect. All right. So we're going to do the same thing for every point in validation data, and for every point in validation data, add the new list to validation. So we're going to do something very similar here. If we can honestly just copy and paste this for a second. I am going to, well, let's just, for the sake of the training, let's just do it all over again. I am going to create another for loop, for point in validation data. I am going to now print point and then break. Again, it just prints out a point, so I know I'm doing good. So now we can do the same thing where we're going to create a new list object and then new list dot append, and this is where we can do the same 2 times or 2 to the power of 1/2, which is the square root, times point at index 0 times point at index 1. In the next one, we'll do new list dot append, and we'll take the point 0 and raise it to the power of 2. Last one for the new list appending, append point at index 1 to the power of 2. Now we're going to then finally do new validation dot append with this new list object. So we've done that now. We can now retrain classifier by calling the fit method using the new training and new label and training labels as parameters. So we can do this by doing classifier dot fit, and we will do the new training and the same training labels. And we can now finally run, and I assume it'll want me to print it out, so we can do classifier.score on the validation data and the oh no, it's actually, we want to use the new one, so new validation did all that work, don't want to not use it, right? And validation labels, and we did it nicely. Ended up being 100%, which is something that I'm very happy with. obviously. When we originally did it, it actually got only a 56% score, but this one got 100%, so obviously what you'd love to see. Radial basis function kernel. The most commonly used kernel in SVMs is a radial basis function, RBF kernel. This is the default kernel used in scikit-learn's SVZ object. If you don't specifically set the kernel to linear poly, the SVC object will use an RBF kernel. If you want to be explicit, you can set kernel equal to RBF, although this is redundant. It's very tricky to visualize how an RBF kernel transforms the data. The polynomial kernel we use transforms two-dimensional points into three-dimensional points. An RBF kernel transforms two-dimensional points into points with an infinite number of dimensions. We won't get in how the kernel does this, but it involves some fairly complicated linear algebra. However, it is important to know about the RBF's kernel gamma parameter. So gamma is similar to the C parameter. You can essentially tune the model to be more or less sensitive to the training data. A higher gamma, say a 100, will put more importance on the training data and could result in overfitting. Conversely, a lower gamma like 0.01 makes the points in the training data less relevant and can result in underfitting. We're going to be using an RBF to draw a decision boundary for the following points. This one's obviously going to be pretty tricky. We've imported the data for you and split it into training data, validation data, training labels, and validation labels. We'll begin by creating a SVC object called classifier. So very similar to what we've been doing. And in this, we want it to have a kernel. We'll specify that the kernel is RBF, even though this is, again, redundant. And we'll set gamma equal to 1. So when we do this, we'll have to now train the data using classifier.fit. And we'll use the training data that we have been given, training labels. So now it wants us to print the score, so we can do print classifier.score using the validation data and validation labels as parameters. It looks like we have roughly an 88% chance, a little bit higher, maybe around 89. Let's see what happens when we increase the gamma, though. If we increase it to 10, what happens? It actually goes down. The accuracy actually went down. We overfit our model. Now let's change the data the gamma to 0.1. What happens then? Oh, it went down even further. So we can kind of see that our original gamma of 1 was the best predictor in finding in actually being accurate. All right, great work. Here are some major takeaways from the lesson. SVMs are supervised machine learning models used for classification. An SVM uses support vectors to define a decision boundary. Classifications are made by comparing unlabeled points to that decision boundary. Support vectors are the points of each class closest to the decision boundary. The distance between the support vectors and the decision boundary is called the margin. SVMs attempt to create the largest margin possible while staying within an acceptable amount of error. There's also a couple other things like the C parameter. SVMs use kernels that classify points. Doesn't always have to be linear, right? We can transform points into a higher dimensional space. Polynomial kernel transforms those points into 3 dimensions. And we also use the gamma parameter to kind of fit the model a little bit better. Got a little bit of XP in computer science, data science, and machine learning, my 3 favorite categories. So let's do this. What is the role of a kernel in an SVM? Kernel chooses what data point should be in the training set and what should be in the validation set. That's not the job of the kernel. Obviously, that's in this split, right? The kernel sets the margin of an SVM to be either a hard margin or a soft margin. That's also not necessarily true. That's the C value, right? A kernel transforms the data into higher dimensions so it can be linearly separable. That's true, but it was true for the poly kernel, but a kernel helps find the support vectors quicker. Is interesting. I'm going to go with this one. Yeah, kernels help make decision boundaries for points that are not linearly separable. Why is it so important for an SVM to maximize the size of its margin? A large margin makes it more the size of the margin doesn't matter as long as the data is linearly separable. That's not true. A large margin prevents points in the training set from being close to the decision boundary. A large margin makes more of the training points relevant, and a small margin results in underfitting. Yeah, this one. An SVM has a soft margin when the margin is small and the decision boundary allows for few errors. The support vectors are the points furthest away from the decision boundary. The support vectors are the closest points from one class, not both. The margin is large and the decision boundary allows for many errors. So an SVM has a soft margin when the margin is small and the decision boundary allows for few errors. That's a hard margin, right? The margin is large and the decision boundary allows for many errors. That sounds more like a soft margin. What are the support vectors in an SVM? All the points in the training set on one side of the decision boundary, points in the training set that fall directly on the decision boundary, the points in the training set closest to the decision boundary. Yeah. What happens to a support vector machine if C is too large? If it's too large, we're overfitting our data. Because overfitting will occur due to the margin becoming too small. If C is too small, then the margin will be large and underfitting might occur. Okay. If your data is in 3 dimensions, a decision boundary will be a plane. That makes sense. Which of the following SVMs has the optimal decision boundary? This one, letter A looks the best option just because it is the farthest away from both sets. So I'm going to go with A. Has the largest gamma parameter. So let's think about that. I'm going to say probably A has the biggest gamma. It's actually C, so it's the opposite in that case. So that was a bit of a mistake there. What are the inputs of the .fit method in the SVZ class? There's 2 inputs to the fit method. One is a list of the training points and a list of the labels associated to that point. So this one. So we got that right. Let's go to number 5. What happens if the value of C in a support vector machine is too large? The margin becomes too small, leading to overfitting. The other one we got wrong was the gamma parameter in an SVM with RBF kernel controls the influence of a single training example with higher values leading to more complex decision boundaries. Therefore, choosing the SVM with the largest gamma results in the model with more intricate decision boundary, which can better fit the training data. But to data science and machine learning. Cool. And it looks like we have a project, and it's predict baseball strike zones with machine learning. Support vector machines are a powerful learning model that can make complex decision boundaries. An SVM decision boundary can twist and curve to accommodate the training data. In this project, we will use an SVM trained using a baseball data set to find the decision boundary of a strike zone. The strike zone can be thought of as a decision boundary that determines whether or not a pitch is a strike or a ball. There is a strict definition of the strike zone. In practice, however, it will vary depending on the umpire or player at bat. Let's use our knowledge of SVMs to find a real strike zone of several baseball players. All right, creating the labels. We've imported several data frames related to some of baseball's biggest stars. We have data on Aaron Judge and Jose Altuve. Judge is one of the tallest players in the league, and Altuve is one of the shortest. Their strike zones should be pretty different. Each row of these data frames corresponds to a single pitch that the batter saw in the 2017 season. To begin, let's take a look at all of the features of a pitch. Print Aaron Judge.columns. So we can do that very simply by printing Aaron_Judge.columns. When we do that, we see that there are so many different columns. In this project, we'll ask you to print out a lot of information, void clutter, delete these print statements once you understand. We used the PyBaseball package to get data for this project. If you're interested in getting more data, the documentation for PyBaseball can help you get data you're interested on your own computer. Some of these features have obscure names, so let's learn what the feature description means. All right, so next I'm going to print Aaron Judge dot description dot unique. So he could have a swinging strike, called strike, a ball hit into play and scored, a foul, a blocked ball, a hit into play, no out, and a strike, swinging strike blocked, foul tip, and hit by pitch. We're interested in looking on whether a pitch was called a ball or a strike. This information is stored in the type feature. Look at all the unique values stored in the type feature to get an idea of how they are called. Yeah, I was just going to say probably type. So it's either an S, a B, or an X, right? So a S is for a strike, B is for a ball, or X for neither. For example, an X could be a hit or an out. We'll want to use this feature as the label of our data points. However, instead of strings, it would be easier if we changed every S to a 1 and every B to a 0. You can change the values of a data frame using the map functions. For example, in the code below, every A in example column is changed to a 1 and every B is changed to a 2. So that's what it wants us to do. We want to, in the type function, we know every row's type, so it wants us to do, the data frame is Aaron Judge, right? So we want to change, we want to change Aaron Judge's, what's it called, type column. We'll do this. To do this, we'll do data frame and, oh my goodness, Aaron Judge at the index of type dot map, and we'll add the dictionary here. So for every time there is the letter S, it wants us to map a strike to a 1, and it wants us to map a ball to a 0. So doing that, we can now also comment this out. We don't need that anymore. But now if we print the type column from Aaron Judge, we can see that it should be a bunch of 1s and 0s. So yep, we see a bunch of 1s and 0s, which is amazing. We do see a couple of NaNs, and that's possibly, if I had to guess, for the X's, which could be a hit or an out. There are some NaNs in there. We'll take care of those in a second. For now, let's look at the other features we're interested in. We want to predict whether a pitch is a ball or strike based on its location over the plate. You can find the ball's location in the columns plate X and plate Z. Print Aaron Judge's plate X column to see what the column looks like. So we can do that pretty easily. We can get rid of the type and instead put plate underscore X. So it's saying plate X measures how far left or right the pitch is from the center of a home plate. If plate X is equal to 0, that means the pitch was directly in the middle of home plate. We now have 3 columns we can work with: plate X, plate Z, and plate type. Let's remove every row that has NaN in any of those columns. We can do this by calling the drop NA function. So this function can take a parameter named subset, which will be a list of columns you're interested in. For example, the following code drops all the NaN values from the columns A, B, and C. So it's kind of telling us how to do it. It wants us to say, it's going to say Aaron, we want to take the Aaron Judge data frame, and we'll do Aaron Judge dot drop NA from the a list of these. So the first one is the plate X column. The next one is the plate underscore Z column. And finally, we are going to get rid of anyone that is in the type column, right? So we're going to use that function to drop all the NaN values. Ooh. Where am I getting issues here? So let's quick comment that out so we can just take a look at what the error is saying. Line 15 it's having trouble with. So it is in this drop NA function. Let's see if I did this. I didn't specify subset. Subset is equal to. I missed this little keyword here. That was my mistake, obviously. We now have points to plot using matplotlib. Call plot.scatter using 5 parameters. So we can do plt.scatter using 5 parameters. X should be equal to plate X. Y should be equal to plate Z. To color the points correctly, the parameter C should be the type column. Probably have to do that. To make the strikes red and the balls blue, set CMap equal to plt.cm.coolWarm. We'll set also alpha equal to 0.25 to make it a little bit more transparent. So now we can do plt.show. Plate X is not defined. And that is very obviously a mistake on my part. I should have specified that this is the column that I want to access. So obviously the parameter plate Z does not exist. Plate X is not defined, and this is in line 16. It's saying, what are we doing here? Now this should be good. And now I'm getting more errors than I've ever seen in my life. Okay. Why is it struggling here? So let's see. I think I did this right. X is equal to Aaron Judge at plate X. Equal to Aaron Judge at plate Z. C is equal to type. Yeah, it's type. What am I doing? Aaron Judge at type. And now it looks great. So we can now see that we need to build the SVM. We can kind of see that there is a little bit of ease in here. Well, or not ease, what am I saying? A little bit of a pattern going on, I'd say. The inner ones are more red, the outer ones are more blue. So we've seen the location of every pitch. Let's create an SVM to create a decision boundary. This decision boundary will be the real strike zone for players. For this section, make sure to write all of your code below the scatter function, but above the show function. So again, all the code is going to go in here. To begin, we want to validate our model, so we'll need to split the data set into using the train test split. So we'll say training data, validation data, training labels, and validation labels is equal to train test split with the function using Aaron Judge as a parameter. I'm going to set the parameter random state equal to 1. The function should return to object, store the return values and variables naming. So it doesn't want the labels. It just wants training set set and validation set. Next, create an SVC object named classifier. SVC. We're going to set kernel equal to RBF, even though that is redundant. Something that we have seen today is that's very redundant. And we'll also set, it says right now don't worry about setting C or gamma. So we've done this, call the fit method. So we can do classifier.fit, 2 parameters. So training data, so it just wants me to select the 2 columns. So for the first one, we're going to say Aaron Judge, columns, plate underscore X and plate underscore Z. And the second parameter in the fit function will be the column type. So we can just do Aaron Judge at the index type. To visualize the SVM, call the draw boundary function. This is a function that we wrote ourselves. You won't find it in scikit-learn. The function takes in 2 parameters. So it wants me to, I guess I can get rid of some of that. But what it wants me to do, I'm going to kind of just move them apart so you kind of get a better idea of what I'm doing in the same step. To visualize the SVM, call the draw boundary function. This is a function that we wrote ourselves. It takes in 2 functions. So it's called the draw boundary function. The axis, this is the AX variable. And then the second one, classifier. Run your code to see the predicted strike zone. It is taking a second to load here. All right, it looks like it has created the boundary where there is a very small center, and then outside of that is blue. Run the code to see your predicted strike zone. Note that the boundary will be drawn based on the size of the current axis. So if you call boundary before scatter, you will only see the boundary as a small square. To get around this, you could manually set the size of the axis using something like axis.setLineLimit before calling boundary. All right, optimizing the SVM. Nice work, we'll be able to see the strike zone, but we don't know how accurate our classifier is. Let's find out by calling the .score function and printing the results. So we can do that by doing print classifier.score. The 2 parameters should be very similar. 2 parameters, the validation. I actually want to see what this is. I see. This actually shouldn't be Aaron Judge then. This should be training set. And now we can do .score using validation set of plate underscore X and plate underscore Z, and then validation set don't have a bunch of errors. Did it right. About 83% accurate. Let's change some of the SVMs parameters. So now we're going to go back up here to SVC, and we're going to add some more parameters. We're going to first put gamma is equal to 100, and we're also going to put capital C is equal to 100 and see what happens. This will obviously overfit the data, but it's a good place to start. The new accuracy, again, the old one was about 83%. The new accuracy is a little over 79%. Try to find a configuration of gamma and C that it greatly improves. You may want to use nested loops. Loop through every different value of gamma and C and print the accuracy of those. Our best SVM had an accuracy of 83.41. Gamma is equal to 3. I don't really want to create a new for loop, and I really don't have to. We'll just use their one. Explore other players. Aaron judges the tallest player. Jose Altuve is the smallest player. We could also do him instead, but I'm going to kind of skip that just for today, so we're not sitting here forever. All right. We'll now add on this little linear discriminant analysis article here because it's not kind of fitting anywhere else in the next video. I'm not just going to do one video based on this one slide, basically. Linear discriminant analysis. Learn about the linear discriminant analysis, a dimensionality reduction technique for classification problems, how to implement it in scikit-learn. Introduction. Linear discriminant analysis, LDA, is a dimensionality reduction technique used for classification problems with continuous independent variables. This technique can be used in a wide variety of applications, including image recognition, marketing, biological classification, and more. It works by using linear algebra techniques to find a subspace within the space of independent variables that simplifies classification problems. So how LDA works. Let's start with a simple example. Here's a classification problem with two continuous independent variables and two classes, a red class and a blue class. In this example, you could easily draw a line that would separate most of the data points from red and blue ones. But how could you simplify the problem? By reducing the data to a single dimension. If we project the data onto a one-dimensional subspace, we might be able to separate red from blue with only one dimension instead of two. Here, there are two different ways of projecting the data onto one dimension, here and here. In the first example, there's no good way to separate the blue from red, but in the second, you could easily choose a good decision boundary. This second subspace isn't just any subspace, it's actually the subspace that does the best job of separating red and blue. It was obtained by using LDA. This is what LDA does in general, but it finds it finds the best possible subspace for a given classification problem. When there are only two classes, LDA finds a subspace that maximizes the variance between the classes within the classes. This means that it finds a subspace where classes are far apart from each other, but the observations within individual classes are close to each other. LDA can also be applied when there are more than two classes, but this is slightly more complicated. Once LDA finds the best subspace, data points can be projected onto that subspace. This yields a data set with fewer dimensions, but nearly as much predictive power. LDA can also be used as a classifier by itself with the additional step of computing a decision boundary. Notice that LDA is similar to principal component analysis, PCA. Both LDA and PCA are dimensionality reduction tools. They both reduce dimensions in a similar way by using linear algebra to find optimal subspaces for a statistical or machine learning problem. A key difference between LDA and PCA is that they have different applications. PCA uses linear algebra techniques to find a subspace that maximizes the variance of a dataset. This means that PCA basically finds the subset that is best for linear reduction or regression problems. LDA, on the other hand, uses linear algebra techniques to find a subspace that is best for classification problems. Which of the following statements about linear discrimination is false? Discriminant analysis is false. LDA uses linear algebra in their two classes. Use an alternative. LDA can only be used for classification problems where the dependent variable is discrete. Okay. All right, implementing it with scikit-learn. The original data set contains, so it's kind of teaching us another data set here. It seems a little bit too much. Maybe it was probably better off as something else. Conclusion, in summary, LDA is a powerful, yeah, just another technique. Okay, cool. Some more stuff in Python, data science, everything like that. That is going to do it for today's video. If you did enjoy, please be sure to leave a like and subscribe. I'll see you in the next one. Peace out.